And so now when I'm looking at this, all right, I could separate this out and I could say the limit of x to the fourth times the limit of what's in the parentheses using our properties of limits, right? Or I can just come in and say, okay, what I have if I'm looking at this now is going to be the limit as x goes to negative infinity of x to the fourth would be what? Negative infinity to the fourth power times 2. But here we've created those facts, right? We know that this fraction here, 1 over x squared, is going to approach 0, right? It goes to 0 because the denominator is getting larger. This one over here goes to 0. So I end up with 2 times what is negative infinity to the fourth power? Positive infinity, right? Okay. So I end up with positive infinity in this case. Now we can actually have a number times infinity, but the indeterminate case that we're not allowed to have is infinity minus infinity, because some value here times infinity is just making that number larger, isn't it? Infinity minus infinity, if you wrap your head around that one for just a second, is a lot harder to pinpoint, isn't it? Okay, this one's actually okay. This is not an indeterminate case. But it's an illustration of, okay, well, if we can't use direct substitution, and there's a reason why we can't, because we have an error with it, can I now, instead of maybe thinking about dividing by 1 over the highest power, why don't I just think about factoring out the highest power? It's the same thing. When I divide, that's the same thing as multiplying by the reciprocal, right? Or when I factor, I should say, that's the same thing as multiplying by 1 over, right? When I divide. Okay. Now, the reason I want to do this is because I want to and we're going to practice it on this one as well. As we lead into the example that'll be new for you today, it might make a little more sense. So let's look at this one. This is another one that we were talking about yesterday, where we have this rational function that we're taking the limit of as we approach infinity, negative infinity again. And in this case, if again, I was to plug in direct substitution is going to yield me what? Infinity over a negative infinity in the denominator, right? Yeah, if I just direct substitute in there. This is the other case. There's 3 total cases, maybe, or 4. That's another case that we're not allowed to have. This again is an example of an indeterminate case. So we can't have subtraction of or addition of infinities, and we can't have division of infinities. So because that doesn't work, we were working on yesterday, okay, well, how do we do this? Yesterday we said we would take the power in the denominator and we would multiply by the top and the bottom by 1 over that power. So today let's change that thinking just a little bit, and instead let's consider multiplying top and bottom by the highest power, or factoring out, excuse me, top and bottom by the highest power of the denominator. Okay, so in the numerator, we would have the limit as x approaches negative infinity of, now I'm going to factor, we already did this above, but I'm going to factor x to the fourth out, leaving me with 2 minus 1 over x squared minus 8 over x cubed divided by, factor out in the denominator as well, x to the fourth times negative 5 plus 7 over x to the fourth. Still picking the highest power of the denominator, but I'm going to stick with the denominator and factor that highest power out. I stick with the numerator and I factor its highest power out. Now I can cancel both of these factors here because x to the fourth over x to the fourth cancels. And now I can come in and address my limit as x approaches negative infinity. So in the numerator, we would have what? 2 minus 0 minus 0 like we had above. In the denominator, we would have -5 plus 0 for that second term. And we would end up with a horizontal asymptote at -2/5. Same thing that we did yesterday, I'm just approaching it a little bit differently, and I'll show you why it maybe makes a little more sense in a minute. Does everybody agree with that? Yeah? Kind of a rehash anyway of what we did yesterday as far as taking the limits are concerned. Questions on that? No?
So would it be like defining the range, I guess? Because if the rational one, horizontal asymptote is -2/5, all the other one just gives infinity. Kind of be what we're looking for in a sense.
I don't know, I didn't think about that. I'm thinking of it that way, and I don't know. Okay. Let's look at this one right here. It's a rational function. But it's nasty looking, isn't it? It's got a square root in it. I changed it. Right, I changed it. It's got a square root in it, all right? But we're going to approach it in the same fashion that we were just doing a minute ago. So let's first take this function, and if we're looking at the denominator, right? The denominator is what's guiding us on this. What's the highest, what would I factor out of the denominator? All right, so I would factor an x out of the denominator. I'm gonna start there. So I would have x, and I'm left with 5/x minus 2. Now, in the numerator, I'm going to, and I just want you to follow along for just a second here. Here, I have x squared. I'm going to factor that x squared out but I'm going to stay under the radical sign. So if I have x squared times 3 plus 6/x squared, right? And there's a reason why I'm doing this. Let's look at the numerator again. The numerator could be written, let's say, as the square root of x squared times the square root of 3 plus 6/x squared divided by what we had in the denominator, minus 2. So far, so good. I didn't do anything except separate my two square root factors. But now what's the square root of x squared? Okay. It's not exactly x. It's absolute value of x times the square root of what we have. Yes. Now here we have x and 5/x minus 2. Okay. So we have the idea that I'm going to call it the absolute value. We just inherently take either the plus or the minus value, right? But if we can think of it in this term, if I'm taking this and whittling it down to an absolute value of x, I want to show you how that's going to help me take the limit as I go to negative infinity versus the limit as I go to positive infinity, okay? So does everybody at least understand how I got to this point right here? You'll notice that I'm going to be able to, I wanted these two x's, even though that's in an absolute value sign right there, I wanted them to be the same power, right? Okay, and it's just not something that you normally consider. If I'd have started back here and we went down the route we did yesterday, you would have been multiplying top and bottom. You would have multiplied the top by 1/x squared and the bottom 1 over the square root of x squared and the bottom by 1/x. Did you even understand what I said? Yes, see, it's like, whatever, I don't even know what you're talking about. Okay, Now, this is the function that we're going to take the limit of to either negative or positive infinity, okay? So let's address the limit as x approaches negative infinity. If x is going to negative infinity, x must be negative, right? If x is going to negative infinity, x must be negative. So we can put this negative x here times the square root of 3 plus 6 over x squared divided by the denominator. We chose negative x because I'm going to negative infinity. Now the x's cancel. And I'm left with, I'll go down here, the limit as x approaches negative infinity of the square root of 3 plus 6 over x squared divided by 5 over x minus 2. Yes, thank you. Put a negative on there. All right, we put a negative on there. Now, here I have negative square root of 3 plus 6 over negative infinity squared is still going to be 0, right? Okay, 0 divided by 5 over negative infinity is still going to be 0, right? Minus 2. So we have negative square root of 3 over 2 over negative 2, or in other words, a positive square root of 3 over 2, correct? Okay. Now we're going to do it again, taking the limit as we go to positive infinity. All right? So the limit as x approaches positive infinity. So if x is going to positive infinity, then I take x to be positive, right? So I'm going to put a positive x here times the square root of the whole thing again. And it's a similar process. Those x's are going to cancel just like they did before. So I have the limit as x approaches infinity. 3 plus 6 over x squared divided by 5 over x minus 2. 6 over x squared goes to 0. So I have the square root of 3 in the numerator, negative 2 in the denominator, or I have negative square root of 3 over 2, right? Now, these are both going, when I take the limits, I take the limit to negative infinity and I get positive square root of 3 over 2, okay? So I have a horizontal asymptote at positive square root of 3 over 2. And when I take the limit going to positive infinity, I have this one, negative square root of 3 over 2. You've seen those and you can graph them. It's just kind of bounded, right? Where we might have some curve that is a logistic curve, maybe even, okay? I think it's a little clearer whenever you're looking at these square roots, all right? Whenever we're looking at these square roots, I think it's easier to start by focus on your denominator, right? I needed to factor out an x, okay? And then, you know, what we eventually want is an x in the numerator, but how do I get there? I gotta kind of go through these steps. Would I need to do this? I only need to do this when we're thinking of even roots, right? Square roots, fourth roots, sixth roots, and so on, because odd roots, I can always take the negative. I mean, I can take the cubed root of -8, can't I? Okay, so odd roots, you don't care if there's a negative sign. Even roots are the ones that we care about there being an issue with. Okay, all right. You see that, you know that paper that you were working on in class yesterday up at the board? All right, very quickly, I want you to practice this on question number 8. So then question number 8 right there on your paper, I want you to practice that. Using the same thing I just did. So follow along with what I wrote down. And then if you think you've got that answer right, go on and try your hand at the next one. Remember, the denominator is what leads us to what we need to be doing. You can't separate this from the division. And you have that, you can only separate the first factors, which is why we factored out the x squared.
Oh, yeah.
Yeah, is it there? That's why we factored out that x squared. Take the limit to both negative and positive. Are you gonna know that there's gonna be a negative something like that, just cancel out? So one time you have to make it a negative x, and as long as you make sure you make it as a negative x and positive x. That's what the absolute value was from, that I can have both a negative and a positive value for x. Not interested. The only reason I don't have an absolute value down here is because I'm taking the square root of x squared. It's positive and It's for the absolute value wash. If you can remember, when you take, if you want to write that instead of absolute value bar, you can put a plus and a minus.
Oh, I guess it is because you can take those.
All right, and if you get one of them, see if you can practice that last one underneath it. You just did that. But you took this up from the wrong one. So 7 divided by x squared, you just have to put. Just the numerator is correct. These are horizontal. I don't know.
So
Yes.
you only make the plus and negative.
And when I go to negative infinity, I use the negative. I
Yeah,
use
but the
negative.
bottom one doesn't.
No, because it's only this x that could have been positive or negative. Right, this x down here is not squared. The reason this is positive and negative is because when I take the square root of x squared, I get both the positive and the negative values. Are you trying the other one too? Does it make sense what we're talking about? It's kind of weird looking, but
Weird looking, but it makes sense. At least as of right now, so it's.
most of you got that answer, positive and negative 3/2, right? Y would be equal to positive and negative 3/2 if I wrote the equation for the horizontal asymptote, right? Okay? And we have another minute or so, so go ahead and try that last one down there. Again, it's the denominator that's leading this. Number 9 is the one I'm asking y'all to try, if you've already finished the 7. No, 8. If you've already done 8, do number 9. That makes sense. Did you do 10 also? As well. While you're doing this, practicing. So this idea of factoring out the highest term in your denominator holds true for those rational expressions we did yesterday as well. If I factor something out, that's the same thing as multiplying by 1 over that value. We're just approaching it maybe a little bit different, and I kind of think it looks a little cleaner.
So you factor out x squared. That's 2.
Okay.
3 over x squared. That's 0. So when it's negative infinity, just negative and 10 from the, just negative 2. This is 8.
It's negative square root. This is all in your square. Other than that, I think.
No. Yeah, okay. Yeah.
All right. All right, are we ready to move on? You want to see the answer to number 9? Here's the answer to number 9. You should have found that as x approaches negative infinity, you get negative square root of 2 over 2. And as x approaches positive infinity, you should get positive square root of 2 over 2. Okay? All right, I hope that's a little bit cleaner and clearer from what we were talking about yesterday. Sure, Ms. Key, it was. I'm so glad to hear it. Yes. Good.
Steps to it. Not get lost in the-
Okay. All right, let's continue on with these limits again. So those that we were doing just now, when x is going to positive or negative infinity, we said that we're talking about horizontal asymptotes in essence, right? And what we're going to turn our sights to right now is an infinite limit. All right, and so you can see that what we're looking at here is when we're thinking of infinite limits is as x is approaching some constant, right, as we're getting closer and closer to some value, then we have limits that are moving off to positive infinity, or negative infinity. In other words, we have vertical asymptotes now, all right? So before we had horizontal, now we're talking about now we're talking about vertical asymptotes. And so if you're thinking about, why are we looking at this if I already know how to find a vertical asymptote on a rational number? What we're doing is in essence proving through calculus, right? Somebody had to come up with how these things work and make it easy for us in pre-cal, all right? So what we're looking at from calculus is why do I end up with that horizontal asymptote? Why do I end up with that vertical asymptote? Okay, so although we can usually see what's happening and we kind of know where these vertical asymptotes are, what I want you to consider instead is, can I prove it through calculus? Can I prove it through a limit that yes, there is indeed an asymptote here that we're looking at? All right. So we want to take limits as we approach a single number, right? That's kind of what we're looking at here. Okay, I want to know what's happening as I get closer and closer. Our formal definition of a vertical asymptote says that I can define a vertical asymptote if I have either the limit as x approaches this a of the function goes to positive infinity or negative infinity, all right? That's the definition then of a vertical asymptote. So again, even though we may know what the vertical asymptote is going to look like, can I show it through limits is what we're looking at here. So what I first want to look at here is this function f of x, which is equal to 3 over 4 minus x cubed. All right, and we're going to see if we can look at this. We want to take the limit of this function. I want to take the limit of this function as x approaches positive 4 from the right. Now I jumped into that because I didn't have it written down, I just knew. What's the vertical, where is the denominator undefined, everybody? Look at the denominator, it's undefined at 4, right? We know then that because this is undefined at 4, it can't cancel with anything from the numerator, there's no hole there. This has to be a vertical asymptote at x equals 4, correct? All right, so if we know that there is a vertical asymptote when x is equal to 4, let's prove it using limits that as I approach 4, I'm gonna go to positive or negative infinity, all right? So the limit as I move to 4 from the right of 3 over 4 minus x to the 3rd power. So if I have the number 4 here and I'm getting closer to 4 from the right, then I'm gonna kind of substitute in a number. This is helping me kind of keep these things straight, right? So I can look at this and go, okay, well, let's just pick a number to the right of 4, like 4.1 or 4.5 I chose, whatever, 4.1. So I would have 4 minus, this is just a, let's try out some numbers. 4.1 cubed. So in the numerator, I've got 3, which is positive, correct? 3 is positive. That's why I'm going to put a positive sign up there. In the denominator, what happens when I subtract 4.1 from 4? I get a negative value, don't I? 4.1 is larger than 4. And if I cube that negative value, I end up with a negative value, right? So this is what I'm considering here. Is my numerator and denominator, are my numerators and denominators positive values or negative values? I don't really care what the number is, I just want to know if it's positive or versus negative. I know that as I get incrementally closer and closer and closer to 4, the numbers are going to go towards infinity, right? I have an infinite number of values I can choose in that way, right? This tells me the sign of what's happening. Positive over a negative is a negative, correct? So this says that my function is approaching negative infinity if I am coming to 4 from the right. Right, so I would be going down, okay? Because I'm going towards negative infinity, okay? And you can just, until you get good with this or until you feel comfortable with this, just kind of do some table of values and see what happens, all right? Let's look at the limit as x approaches 4 from the left of this function. 3 over 4 minus x cubed. So I've got 4 here and I'm approaching it from the left. So if I just kind of test some values, test a value, then I would say 4 minus, let's go 3.9. That's just a number. It's a number that's less than 4, right? 4 minus 3.9 is positive, correct? Okay. So in the numerator, that 3 is still positive. In the denominator, a positive value raised to the 3rd power is still going to be positive. And all we're looking at is we know this is going to go to infinity, but in which direction? And because a positive over a positive is a positive, we would say that as I move towards negative, as I move towards 4 from the left, I'm going to positive infinity. Okay. So that's what we're looking at when we think of this as we're approaching this. Now, if I asked you what is the limit as x approaches 4 of my function above, what would you tell me? Does not exist because it's from the left, it's 1, from the right, it's another, right? It does not exist because the left and the right limits are not the same. That's if I just want to know what the limit is. However, either of these statements above, taking the limit as x approaches 4 from the right, or taking the limit as x approaches 4 from the left, showed that the limit goes to infinity, whether it was positive or negative, and therefore that shows that it is in fact an asymptote, according to our definition above, right? We have a vertical asymptote if, as I take x towards that value of the function, you get to either positive or negative infinity, according to the definition. So we proved it in essence, using limits. Okay? All right, let's practice some of these. That's the goal of what we're looking at for limits that go to infinity. Limits that go to infinity. So in other words, the limit at some value going to infinity are vertical asymptotes. So here I have the limit as x approaches 1 from the left of x squared minus 3x all over x minus 1. It's a rational function. If I were to factor this, I don't have any common factors, so I don't have a whole, okay? But I know then that I can take that denominator right there, and that denominator says that we have a vertical asymptote when x is equal to 1, correct? That's why we're taking the limit as x approaches 1. So the limit as x approaches 1 from the left. So I need a number, I'm gonna pick a number that's smaller than 1. Let's go with All right, 0.9 squared minus 3 times 0.9 divided by 0.9 minus 1. So in your calculators, tell me what's 0.9 squared minus 3 minus that. What's the numerator? It's a negative value, okay? So I end up with a negative number when I am testing this out in the numerator. And then I can see in the denominator 0.9 minus 1 is also negative, right? Okay. So this tells me then that the limit as x approaches 1 from the left has to be positive infinity. All right? How can you check this? Go at your calculator, right? Try to see the graph. Okay, look at that. Look at a table of values. Okay, really just trying out different values would be helpful. Okay. What if I wanted to look at this? And so just by doing it in one direction, we've been able to say that yes, this is indeed a vertical asymptote at x is equal to 1. We've met the definition, in other words. How about this next one? This says the limit as x approaches -4 from the right. I'm going to factor this so I can kind of see what's happening here. In the numerator, I can take out a negative x. I'm left with x squared minus 5x plus 6 divided by, take out a negative x squared in the bottom. And I'm left with x plus 4. So I can simplify this a little further, and I end up with x squared minus 5x plus 6 in the numerator over x times x plus 4 in the denominator, right? I just canceled that x. The x from the numerator canceled with one of the x's in the denominator, and the negative signs canceled each other out, didn't they? So I kind of just cleaned it up before I want to go any further. So now let's take the limit as x approaches -4 from the right. We can see in here that we have another vertical asymptote at 0, correct? There's another vertical asymptote here, isn't there? All right, that's not the question. The question is asking you to, okay, well, I'm not really interested in that one right now. I want to focus on what the limit is as I approach -4. So I'm technically looking at this asymptote, but I need to use the whole function here to find that limit. So if I want to approach -4 from the right, we want to pick a number that's just to the right of it, don't we?
-3.
All right. So I have -3 squared minus 5 times -3 plus 6 over -3 times -3 plus 4. So 9 plus 15 plus 6 is some number that's positive, right? -3 plus 4 is going to be positive. Times a negative makes a negative in the denominator. So our limit is going to where? Negative infinity. Okay, you all look at it and try it now going to the limit as x approaches -4 from the left. Okay, do we get that the limit as we approach -4 from the left is going to positive infinity? Okay, so either of those prove that we do have a vertical asymptote at -4. You don't have to do both of them to prove it. You had to do one of them. What would you say though if I asked you for the limit as x approaches -4? It does not exist. Why? Because the left and right are not the same, right? Correct? Okay, all right, I just want to make sure you understand. Everybody understands that these numbers that I'm plugging in, that I'm direct substituting in, are just random numbers that I can use to help me figure that out, right? They're just numbers that are either on the left or the right of C or A, whatever we're calling this number right now, okay? They're just test values, aren't they? Okay. See if you can. Let's look at this problem right here. We have the function x squared minus 4x plus 3 all over x squared minus 1. I'm going to factor that. It factors into x minus 3, x minus 1 in the numerator, x plus 1, x minus 1 in the denominator. So I can cancel common factors. I know I have a whole here, but I'm gonna use the reduced function x minus 3 over x plus 1 to move on and talk about the limits. Right? It's like we're replacing the function with something that's continuous in essence right now, aren't we? Right? We got rid of that whole part, so technically we should be continuous between some areas. So if I want to know the limit as x approaches 1, I can now do that in essence here, can't I? I can direct substitute into the function I just factored. So I would have 1 minus 3 over 1 plus 1. So I would have negative 2 over 1, negative 2 over 2, which would be negative 1, sorry. 1 minus 3 is negative 2, 1 plus 1 is 2. I'd have negative 1. So the limit as x approaches 1 is negative 1. That's what we saw when we were doing limits analytically. If I chose to go back to the very beginning here of my function, and if I was just answering question I directly, could I have done direct substitution at that point?
On the last one.
I couldn't have direct substituted here immediately, could I? Right? So our strategy for solving is to, okay, can I factor it, cancel anything so that now I can use direct substitution, right? That's what we were doing in the algebraic, that's limits analytically. That's limits through algebra. All right. So I now have another question. What is the limit as x approaches negative 1? Right? Now, why do you suppose I want to know that question? Well, if you look at the function that we reduced up here, negative 1 would be our vertical asymptote, wouldn't it? We have a vertical asymptote at negative 1, so let's verify through limits that it's going to go to infinity. So if I'm looking at negative 1 from the left, okay. All right, negative 2. Negative 2 minus 3 all over negative 2 plus 1. Negative over a negative results in a positive, right? So right there, we can see that the function is going to go to infinity, and therefore it's a vertical asymptote. And when we want to approach negative 1 from the right, maybe we could apply 0.9, negative 0.9. Would be negative in the numerator, but positive in the denominator, right? At negative 0.9, because that's negative 0.9 plus 1 would be some positive value. So we would go to negative infinity from that direction. Okay. All right, one more that I want to consider here. This is helpful for when you're looking at these limits. You have a couple of these on your homework. We can find this limit graphically if we remember what this function looked like, right? Let's sketch that graph really fast. Cotangent. Cotangent had an asymptote at 0. And what was the very next asymptote? Pi. So pi. And so we would have a asymptote to the left of it at negative pi, correct? And what did it look like? How would I sketch it? Like a upside down cubic function? Okay. All right, so it's helpful to remember what these look like. You can kind of put that sketch up there. I wanted to know what the limit was as x approached 0 from the right. What is that limit? If I'm coming in
Away from the right side.
positive infinity, very good. How about if I approach it from the left? Negative infinity, that's right. Okay. So I know that you have a couple of problems on your homework where it's asking you to remember what an exponential function looks like, right? What does an exponential function look like?
So
That's exponential, right? Okay, that would be e to the x, we'll call it e to the x, okay? What does a log function, natural log, what's a log function look like? Goes like that, right? Call that natural log x, okay? What else do we know about those two functions? That we have an asymptote here, correct? Or we have an asymptote here, right? So the function is undefined on the other, like, you can't have, it's only defined above that asymptote, right? Or to the right of that asymptote, okay? Also, remember what effect our translations have on things, right? If I asked you, let's say I wanted to know what is y equals e to the, how about negative e to the x? Which way would I reflect that? Over the x-axis, right? So it would look like that, wouldn't it? Going down. What if I wanted to know what negative x this way? Over the y-axis, right? Okay. Remember those translations? All right, that's going to help you out when you're looking at these, when you're trying to remember what it is. If you're trying to do it from a graph, right, and you've got just cotangent x like this, or you have, you know, y is equal to or e is the limit is of e to the negative x, right? Sketch what e to the x is and then reflect it. You don't have to be perfect. You're not turning this in, okay? Just sketch it real fast and see what it looks like and then take the limit because you're talking about it generally going to 0 or infinity or something like that, okay? All right, so that is vertical, horizontal asymptotes, or in other words, infinite limits and limits at infinity. So the last thing that we're going to do is the precise definition of limits. And if we have time for classwork, we'll come back and hit that. Otherwise, we're just moving on. So are y'all awake? Can you go run laps? Did you know I teach a fitness class here? Make y'all do like one of my classes. There you go. All right. So this is the end of our unit on limits. All right. And now that we've been using limits the whole time, oh, let's go ahead and define it. Right. That's really what this is kind of about. It's called the precise limit definition. I'm going to just put this up here for a second. Let you copy that box down because it's important. And it is the formal definition of a limit. And you do need to have this copied down or taken a picture of it because we're going to use these symbols in a minute. So the little squirrely Q thing here, that's delta. That's a lowercase delta. I usually make it kind of like, I don't know, a relaxed 8. I don't know, something like that. It's got a little tail up there. That's delta. This little e over here looks kind of like a smooth little curvy thing right there. That's a lowercase epsilon. So this is why it's called sometimes the epsilon delta or delta epsilon proof. if you were to search delta epsilon or epsilon delta. So it says officially, if we have a function defined by some open interval containing C, and we have a real number L, then the limit as x approaches C of the function is equal to L. That's our basis we've been using, right, the whole time. That was the snippet part of our informal definition of a limit we've been using the whole time. What it gets a little bit further in the weeds on is it says, okay, well, what that means though is that for every epsilon greater than 0, there also exists a delta greater than 0, such that if x minus c is greater than 0 but less than delta, then the absolute value, well, absolute value of both of them, f of x minus L must also be less than epsilon. All I did was reread it for you, okay? That's all I've done so far. So what does this mean? This says, here's a little picture of it. I'll show you in just a second. This says that if I were to take the limit as x approaches c of my function, right? As x gets closer and closer to that middle line, as x gets closer and closer to that c value, okay, then the function must be equal to L, right? That's our limit function. What this says is, okay, well, if that's the case, then if I know that, then what we've got is we've got some distance, some range around L, all right, called epsilon. It's an equidistance, all right? So we have this value here around L, surrounding L, that corresponds then with this range right around, or this interval, let's say, around C, all right? It basically guarantees that. And this is all very interesting, I suppose. Let's put it in terms, I heard this example. So I'm gonna use it because I thought it was kind of clear. Let's pretend that we're gonna play a game of war, all right? We're playing a war game. And over here is a fort, okay? So we have this fort, or a landmark, I should say, all right? So L is gonna represent this landmark, and it's surrounded by walls. And this is my fort. Makes more sense if it's a fort, not a landmark. So here we have that. Now, what we're interested in is we're like let's be the good guys. Okay, so let's say it's a bad fort, right? I don't know why. And we want to be the good guys. So I am here. This is my location. This is our location because we're in this war together, right? I'm here at this location. I need to figure out, where do you suppose we should put our cannons? This is old war. Where do you suppose I should put my cannons so that if I fire my cannons, I'm going to hit their walls? Okay? I'm going to figure out, where do I need to put these things here? Where do my cannons go if it's going to come up here, bounce off of that imaginary thing, and it's going to hit their walls? All right? That's the game we're going to play. Now the walls stay there. The walls are kind of already there. I'm trying to figure out, where do I need to adjust my cannons at to make it to where I hit their walls, okay? Because if I make my cannons too wide, right? If my cannons are too far out here, then I'm not gonna hit their walls, right? Okay, and ideally, I think I wanna be knocking down their walls, not just, and maybe I wanna land a few inside of it because that's war, right? All right. Yeah, you got the idea? That's a much better explanation than the definitions there, right? All right, now what we see is my walls are surrounded by epsilon, right? So the function value L is surrounded by epsilon. And the value C that I'm taking the limit towards are the cannons. All right, where do I put the cannons in order to make it to the wall? Up top. So here I have a function. Let's see, what function is this? This is the function 2x minus 2. All right, and I want to take the limit as x is approaching 4. Right, as x gets closer to 4, the limit is equal to 6. We see that? All right, so as x is approaching 4, the limit of the function is approaching 6. Now, I am defining here, how wide are my walls? Somebody tell me, how wide are the walls on my fort? Right? 1, right? There's a distance of 1 on either side of, I don't know where the captain's at. Okay. Now, notice if I take my cannons and I put them too far away, right? I can shoot my cannons, but I'm not going to hit anything, correct? Okay. So there's this point at which, where do I need to put them at to where it makes, you sunk my battleship, only it's not battleship, right? Same concept. All right, so in other words, the distance now, where do my cannons have to be at? What's the distance for each cannon? 0.25, no, 0.5, because if I have 4 here, yeah, you're right, it's 0.25.
It's going by 2.
3, 4, so this would be 3.5. So it's 0.5, isn't it? Yes, which is what delta says up there. I should have said that, right? So the distance, right? The distance would be delta. Epsilon is distance of 1. Okay? Yes, you're right. Now let's look at. So this is also saying that, in essence, you are wanting to have symmetry around your C, and typically you want symmetry around L, right? All right, so let's practice a couple of these. All right. So if you have these notes, this would be a good time to pull them out because it's pretty easy to do this on your notes. It says, here I've got a graph, and I want to show that we've had the graph of a linear function, and we're taking the limit of that function as x approaches 3, and the value of the function is equal to 5. So we want to figure out what is going to be the value of delta given epsilon. We've got 2 different values of epsilon that we're using. So we're going to do this twice. So I have to figure out, so if we're given the walls of the fort, we need to figure out where to put the cannons. That's what we're being told here. Okay, so let's identify a couple of things out of this statement. First, we need to know what C is. We need to figure out what C is. Now, C actually comes from 2 different places, but here, if you look back at your formal definition, this inequality statement is related to delta. This is C right here. All right, this is also the same number that we're taking the limit to. All right, so C shows up twice here in what we happen to be looking at. So we kind of maybe want to jot down that C is equal to 3. The value of the limit is what? As we approach 3, the value of the limit's given at the top.
5.
All right, so capital L is equal to 5. Okay, so if I come over here to my graph, right, I know that 5 is equal to L, 3 is equal to C. And in the first statement here, when epsilon is equal to 1. So when epsilon is equal to 1, we are at, on the y-axis, we are at 6 and 4, correct? Because epsilon is equal to 1. So just following the graph over and down. I'm going reverse, aren't I? I'm going from the y direction down. Follow the graph over and down. So it's telling me I would have to place my cannons at 1 and 5, correct? All right, now what is the distance from the center? What is the distance from C to the left or the right edge? The distance is 2. So that tells me that delta is equal to 2. Now you need to check and make sure, we're going to look at an example in a minute, but I want to make sure that delta is most of the time it's going to be symmetric, all right? Most of the time it'll be symmetric. So we figured out, okay, well, the value for delta has to be 2. What will delta be? And does everybody understand that? You're just reading the graph at this point, right? All right, what about if I wanted to talk about epsilon being equal to 1/2? So if epsilon is equal to 1/2, I'm going to start at 5.5 on the y-axis and 4.5 on the y-axis. Bring those pieces down. And so delta has to be equal to what in that case? 1? Yeah? And we all know how to read graphs, but that's what we're looking at. Okay? Just following those down. All right. So that's kind of getting the idea here. How about this question? It's stated a little bit differently. I know you have one like this on your homework. Find an interval, right? I want to know, first of all, I'm given that the limit of this function g of x as x approaches 2 is equal to 3. I'm given 2 separate epsilon values, and I want to figure out what delta is. And then I kind of want to make a generic generalization after that. So we're doing basically the same type of thing here. So here is my function, g of x. And if I just had this sentence, this is at the very top of our screen up there, what value here represents L? Where is L in that sentence that's at the top of the screen, that inequality symbol? 3, that's right. So L is 3. And what is C? Right, C would be 2. Here's 2. So for an epsilon equal to 2, means that I'm going to be at I'm going to be at 5 on the y-axis and 1 on the y-axis. Okay, do you see where we're at now? 5 and 1. Follow those down, and I ended up at 1 and 6. Now I can only place my cannons symmetric. I have to stay symmetric around whatever we're letting C represent. Okay, it's me. Like, I want you to protect me. You only can go this far away from me. It has to be symmetric, all right? What do we do here? Because am I the same distance? C is right here, correct? So I'm a distance of 1 on the left, but I'm a distance of 4 on the right. Okay, so that's not symmetric. And I need it to be symmetric. So you have to choose in this particular case, because of that, we have to actually, we'll be choosing a delta that guarantees symmetry. And so we go with our smallest value. So here, we're gonna use this delta, a delta of 1. Because if I can only move in symmetry, if I can only be symmetric, if I chose this 4, or yeah, if I chose 4 here, then if I went 4 spaces to the opposite side of me, I wouldn't hit them, would I? I would miss them, okay? So because it's not symmetric, we have to choose the smaller value, always. So our delta for this case is going to be equal to 1. How about when epsilon this time is 1? What will I choose then? 0.5, everybody see that? I would have to choose the smaller value, the smaller delta. Okay, for this last component, it says make a conjecture about what you think the corresponding values of delta are that are going to be sufficient for this. In other words, is there a pattern that we can see delta becoming? What do you think it is?
What is it? Goes up, it kind of gets divided by 2.
Right, so it's epsilon over 2, right? Okay, so if I'm looking at this, I would probably make a table of values. If I know that we have epsilon and delta values, and when epsilon was 2, delta was 1. When epsilon was 1, delta was 0.5. The question is about delta. So in other words, delta has to be epsilon divided by 2 each time, okay, in order to get there, as I'm progressively moving down, all right? Okay. How do I handle this then when I don't have a graph? We can actually do this algebraically. So we've got 2 problems here, maybe 3. We've got 3 problems here. So for this first one, all the information I have is given to you here. I'm given what the function is. I'm given what L is, in other words, what the limit is. And I'm given what C is. Okay, that's all I am given, and I want to know what delta is, even though I don't know epsilon. Okay, so we start out by taking that inequality, those 2 inequality statements, the one that y'all are reading from the top of the screen up there. That inequality statement again says that when I take the absolute value of f of x minus L, that's got to be less than epsilon whenever absolute value of x minus c is greater than 0 but less than delta. And that's what we're going to use to be able to kind of work through an inequality statement here. So let's plug in the components to this epsilon side. So the first thing we need to do is we need to figure out what epsilon is, even though we don't really know what it is, but we're going to kind of go with that, all right? So f of x is equal to 4x minus 15 minus L, which is 1. That's got to be less than epsilon. And I'm just going to complete the statement here. And I'm going to say that the absolute value of x minus c, which is 4, has got to be less than delta. I know it's gotta be greater than 0, so I wasn't really interested in that part right now. So if I simplify the left-hand side over here, let's go back to epsilon. And when I simplify this absolute value, I get 4x minus 16 is less than epsilon. I can factor a 4 out, and I would have 4 times x minus 4, which is less than epsilon. And I can even take the 4 out of our inequality statement, and I end up with 4 absolute value x minus 4 is less than epsilon. Or in other words, the absolute value of x minus 4 has to be less than epsilon over 4. Just whittling that down through a bunch of algebra, right? For this type of a problem right here, notice that x minus 4 here is the same as this x minus 4 over here, right? They're the same. So in other words, if these two terms are the same, then we can say that delta must therefore be equal to epsilon over 4. Bless you. So with this particular case, we're trying to find delta, but we don't really know what epsilon is. Okay, we're putting delta in terms of epsilon. So we wanted to see if we could rewrite epsilon with what delta needed to be. And it usually will work out that way. That's your goal. So then the last two that we're going to talk about say that what I want to do is I want to find out what the interval is that contains C. What is the interval that I would put on my, where my cannons would be at, right? So what's the interval that contains C? And then I want to know what is the value then of delta. First, we're going to find the interval, then we're going to find delta. And that's what that says up there. We're going to do it with two different problems here. So the first problem, let's start by writing down that we want to use the absolute value f of x minus L is less than epsilon. That's the first thing that we're going to do. That's number 1. You'll notice that in the given part of this problem, I know the function, I know the limit, I know C, and I know epsilon. So I have everything that I need in order to be able to solve this. So we're going to figure out, using epsilon here, what this interval would need to be. So substitute in f of x, and we get 3x plus 5 minus 20 is less than 0.12. So 3x minus 15 must be less than 0.12. Factor a 3 out, and I get x minus 5 3 times. X minus 5 is less than 0.12. And I am going to solve it from here. Remember when you solve an absolute, yes, sir?
What happened to 20?
Oh, I subtracted 5. 5 minus 20 gives me negative 15. Because 20 is L, right?
Yeah.
All right. So to solve an absolute value inequality, remember that an absolute value can be both positive and negative values, correct? So we would take this as negative 0.12 is less than 3 times x minus 5, which is less than 0.12. I'm gonna divide everything in there by 3. So the left becomes 0.04 less than x minus 5 less than positive 0.04. And then I'm gonna add 5 to everything. So I end up with 4.96 is less than the x, which is less than 5.04. Now, what I think I found is my x, right? This is actually the interval for the x-axis. It's telling me that I'm going to place a cannon at 4.96, and I'm going to place a cannon at 5.04, and in the middle of that is going to be C, right? In the middle of that is going to be C, which is 5. All right, so the interval in interval notation, of course, would look like 4.96 comma 5.04. That's the interval. To find what delta is, we could take the absolute value of x minus c, right? That gives me delta. So in other words, 4.96 minus 5 and 5.04 minus 5. When I do it on the left-hand side, absolute value, right? That's what I'm looking for is distance. I would get 0.04. When I do it on the right-hand side, I get, again, 0.04. Right? We want it to be symmetric. So it is in this particular case. So in other words, delta is equal to 0.04. Okay? If, and I don't have time to work this problem, but if I had time to work the next problem, if you found the interval and yet you plugged it in here just like we did, and these two numbers are not exactly the same, that's our potential delta. Which number am I going to choose for delta? The smallest one, okay? And you'll have a problem like that on your homework, and it typically shows up with things that are not linear, quadratic in nature, square root in nature. You'll have that problem, okay? Think you can handle it?
Could we have just done what you did on the question above it? Just gotten the epsilon over whatever.
Probably.
Yeah.
Yeah.
I mean, yeah, it would.
Okay, now, I'll have your quizzes graded and put in. We're done with limits until later on, and we're gonna start derivatives on Monday. Now, I will have a Desmos lesson for you to look at over the weekend. I need you to get in and practice. I want you to practice just some ideas of connecting graphically a derivative and understanding what a derivative is telling you. Not necessarily how to find it, but what it tells you. All right, so it should be something like that. Your homework is due on Sunday night. All right, you'll have a whole nother round next week with another test or another quiz on Thursday. Y'all have a nice weekend. I'll see you later.